Hello guys, what we have here is a question which was asked in the NET 2011 December exam. The question is that we have a point particle of mass m. Okay, we have here is a point particle of mass m suspended at the end of a spring with a stiffness k or spring constant k, and the mass particle m has a charge q. Okay, if that's the case, then there is an electric field. We are applying an electric field which is turned on at some point of time, and as a result of the electric field, the charge might expand, right? Charge might move in direction. Okay, in this direction, it's in the same direction of the electric field is in the same direction. So as a result, the charge might move against or towards the electric field, and as a result of that, the spring will be extended and the charge will start to oscillate. The mass will start to oscillate. So that's the question. We have the time period of time interval t is equal to root of m by k, and there is no loss of radiation which is neglected at this point. And what we need to find out is the amplitude of this oscillation. So the oscillation amplitude is what we need to find out. Okay, the charge will oscillate as a result of it, and what we need to find out is the amplitude of oscillation. Okay, so first of all, what we can say is that as a result of electric field, the mass is moving. So the force because of electric field is QE, and the restoring force is minus kx. Okay, if it's in the x-axis, if this is the x-axis, then the restoring force will be minus kx. Okay, that's we already are familiar with the concept. Now the total force, which is ma or x double dot, must be equal to QE minus kx. Okay, it's easy as that. So or you can write like this: mx double dot minus QE plus kx is equal to 0, or you can write x double dot plus k by mx is equal to QE by m. Okay, rearranging them. Okay, you can write it like this. So the next thing what we can do is that we get a differential equation right here. We can solve the differential equation and find out x with respect to t, x as a function of t, and we might be getting an oscillating function, some function of cos or sine or something like that, and as a result of that, there will be an amplitude for that equation, and that amplitude is what we necessarily need. So we can solve this differential equation. We can write in the form of a d square plus k by m into 1. In this form you can write as QE by m. Look at this. So you can write the complementary function as what? So d square plus k by m is equal to 0, and d is equal to root k by m. So you can write this equation function in the form of the solution of this function as x equal to c1 some constant into cos root k by m t plus c2 into sine root k by m plus or minus root k by m plus particular integral. So we need to find out the complementary function. We have already found out. We need the particular integral. So particular integral can be found out as 1 by f of d into e raised to ax. So it's e raised to 0 here. So it's 1 by d square plus k by m. Okay, the d square by k plus k by m into qe by m. So the function. So that's how you can write the function. Now another particular integral will become, you can put d square is equal to 0, and qe by 1 k by m will be what we are getting. So it will be qe by m into k by k by m, right? By k by m, by k by m. Okay, so it's QBE QE by K is what we are getting. It's equal to QE by K is equal to M omega, right? K is equal to M omega square. So it's K is equal to M omega square. So that's the particular integral. Now we can substitute back in this equation. We get C1 cos root K by M T plus C2 sine root K by M plus QE by M omega square, which is our solution. There's a T. So T. Okay. So that's our solution, and we can use the boundary condition because at x equal to 0, at t is equal to 0, the shift in position will be equal to 0. X will be at the equilibrium position. So you can use that condition at x equal to 0. Cos 0 is 1, so it's C1 into 1 plus C2 into 0 plus QE by M omega square. So C1 is equal to minus QE by M omega square. Now we can substitute that value of C1 into this equation. We will get minus QE by M omega square because root K by M is equal to omega. Root K by M is equal to omega. We have already said that. So it's cos omega t plus QE by M omega square is our solution right there. We can simplify this solution a little bit. You can say that you can take QE by M omega square outside and you'll get 1 minus cos omega t, and you can substitute for the value as you know already. T is equal to 2 pi by omega, or T is equal to 2 pi by omega, so omega is equal to 2 pi by t. So I'm putting 1 omega. We have our option in T and M, right? T and M and K, so there is no omega here. So what we can do is that we can substitute for the value of omega, and we will get QE by x equal to QE by M into omega square will be 2 pi by t, 2 pi by t, 2 pi by t, right? 2 pi by t or 2 pi by t, so it will be QET by M, QET by M, t is equal to 2 pi by omega. I made a mistake. It's 2 pi by t the whole square, right? Yes, 2 pi by t the whole square because it's omega square. So there is m into, there is an omega also. There is a, okay, I'm putting down 1 omega and a 2 pi by t. So it's 2 pi by t into omega, which is omega square. So it's QET by M into omega into 1 minus cos omega t by 2 pi. Okay, I'm writing it like that because I need an amplitude. So this is the amplitude. So the amplitude will be equal to QET by M into omega, which is omega is equal to root M by K. T is equal to root K by M, right? So omega is equal to, you can write it as root M by K. Omega is equal to root M by K. So that will be root M by K, which will give you QET. I hope it satisfies the size. The root MK. Okay, that's the answer right there. Root MK. So QET by root MK, which is option D right there. So that's the right answer. This was very easy question. It had all the ingredients. It had differential equations, oscillating functions, force, force equations, electric field, and all that. Okay, so it's a very good question from classical dynamics and electrodynamics and all that.